Við erum komin hérna með Kasper Elm Heintz. Hann kemur aftalega frá Kaupmannahöfn til að tala eiginlega upphaf alheimsins og að svara því hvaðan við erum öll komin. Og þetta annar fyrirlestur okkar í fyrirlestrarröð núna í vetur sem við skipuleggjum saman Stjörnuskoðunarfélagið og Stjörnvísindafélagið. Og síðan næst 3. desember þá Jeffrey kemur og hann svolítið að tala hvað sem drífur okkur eiginlega áfram í þessari þekkingarleit sem við erum alltaf í. Svo einhver skrítið kona sem ætlar að vera hérna í janúar og tala stelpur í stjörnufræði. Þetta Harvard-tölurnar og ég valdi 3 merkilegar konur úr þeirra hópi til þess að fjalla sérstaklega en þið munum koma staði þegar við komum að fyrirlestum. Þetta allt yfirskyn til þess að geta að tala bara lita. Ég vona að við sjáum þetta bæði í desember og í janúar en eigum við ekki bara að gera það Kasper? Góðum, gjörðu svo vel.
Let me just quickly change this. Should we dim the light a bit? Or was it too much? Is it all right? Can you all hear me? Okay, good. And well, first of all, greatly apologize that I flew it up in Icelandic. It will really be at your cost if I try. But anyway, so I'll speak English. I hope that's okay. And let me know if there's anything that's unclear. I know 2 or 3 words in Icelandic. Hopefully extrapolate from that. But yeah, so my name is Kasper, and I'm currently an assistant professor at what's called the Cosmic Dawn Center at the Niels Bohr Institute in Copenhagen. And I'm really excited to be here. And again, thank you very much for the invitation. To tell you something about how we are trying to find and characterize the first stars and galaxies in the universe. And it's really exciting in many ways. Most of all, I think, is that this presentation, most of it I wouldn't be able to give like 6 months ago or 3 months ago even. So most of what you're going to see is like actual active research we're doing right now with results coming in all the time. So if you're going to invite me back in 6 months or a year or so, it will be a completely different presentation. So I'm really excited to be here and present some of what we are doing currently. So just a little brief introduction about me. I couldn't understand enough to hear how much you already was told, but I did my master degree in astrophysics at the Niels Bohr Institute, and then I went to Iceland for 3 years, to study at Havli with Palle Jacobsen. Did a few years of postdoc as well before I returned to Denmark as an assistant professor. And I'm really what you would call an observational astronomer, astrophysicist, in that I do some theory, of course. I'm not good at it. I'm not good at math necessarily. But what I'm really good at, or what I really like at least, is to observe the universe in many different ways, find the unexpected and discover something new that we haven't really seen before. And I'm really strongly motivated by using all the biggest telescopes both on Earth and in space now before to try to uncover some of these hidden mysteries in the universe. And just to set the stage, I guess, a bit of what I'm going to talk about, what I work on, which is very broadly the question of where do we come from. And it's a very fundamental question. I think most people have, in one way or the other, let me know if you fall asleep. But I think, so it's one of the fundamental questions that I think most people have at least in some way asked themselves. But it's just to say that we are really actually starting to be able to answer that question like right now, not in like a philosophical sense, but like in actual physical sense, like where are the atoms, where are the heavy elements that make life possible, and all these kind of ways, where did they come from, and when did they first originate in the universe. It's almost like a movie theater. Alright, so again, just to set the stage, I'm going to show a simulation, so it's not actual observations, it's how we expect the early universe to look like. Did you look at it? Yeah. Oh, perfect. So basically, what this simulation will do is that we start the time at 134 million years after the Big Bang. So back then, most of the material after the Big Bang was just some diffuse, mostly hydrogen and helium atoms, that then slowly started around this time to condense and gravitationally collapse into stars and galaxies. So this is Like a few years ago, this was basically the best we could. Like we could only try to predict, so based on what we know from physics and from gravity and so on, this is how we expect the early universe to evolve. You can see already quite rapidly within the first 200 or 300 million years, we start to see a lot of structures already. There's this cosmic web going in, and connecting them are these nodes where all the galaxies and stars form. All these high density yellow, orange-ish nodes, that's new galaxies and new stars forming. And when you see these kind of explosions, that's actually supernova explosions that's creating this very dense gas collapse. So whereas this phase in the picture, we know or expect there to be a lot of hydrogen and helium atoms that collapse together and make some stars. But what I'm going to present today is how to actually measure this. That's something we actually can do now, measure this process, starting from basically nothing, and then making all the stars and galaxies that we see today. So first, before we go there, I mentioned that there are some galaxies in these nodes, and it's really just to highlight that whenever we look up, maybe not from Earth, but like if you have telescopes for your eyes and you're out in space and so on, when you would look up like that, you would see galaxies everywhere. So stars is only a very, very small amount of what you see in the sky, and you can kind of see it already here. So all this spiky, weird-looking objects, those are stars, almost Christmas-like stars, very nice. But almost every object in this picture is a galaxy. So you have like a big galaxy in front here, some down here, some weird-looking galaxies up here. And galaxies, if you forgot from elementary school or primary school, those are structures of millions to 100 billions of stars. They have dark matter, they have supermassive black holes, they have all these exotic physics and constitutions in them. And they're really the cornerstone of modern observational astrophysics. We need to study galaxies to observe where elements and stars form, and we need to track galaxies to figure out how does the large-scale structure of the universe look and evolve. That's why I'm looking at galaxies, at least. So most people are familiar with one galaxy. This was my Icelandic slide, and I really hope it was really nice. Correctly, at least, better brain. How many people have seen that in like real life? Yeah, good. So I think I would expect you to be able to see it in a good night. And in Iceland as well, the caveat being that you have to be in the southern hemisphere of the globe to see the actual center of the Milky Way, so you only see the outskirts up here. But still, you can kind of get this, see this faint wisp of the clouds, almost like structure, because we're in the center of this Milky Way galaxy. But that's a galaxy like many other galaxies that we see, and it's basically the same thing. But now we're just trying to see how does galaxies like the Milky Way, where do they come from, and how do they evolve from the very early universe. But before we do that, I just have to remind you, to maybe something that it's not something you really appreciate going around all the time. But whenever you see something, you always see back in time. Right? So because light has a finite travel time, you will always see something that happens back in time. So now I'll see you guys as you were some nanoseconds ago. I would see whatever that's my next slide here. I would see the sun as it happened 8 minutes ago. That means that whenever the sun is good now, you will never know anything. The sun could disappear right now, and you will only know in 8 minutes or more. Right? The light always travels, and information always travels at the speed of light. So everything you see back in time. And then just going, like just in our own galactic neighborhood, looking at the Andromeda galaxy, for example, which is the closest galaxy to us, you're seeing it as it were 2.5 million years ago. And that's really, that's the closest, that's the best studied galaxies except for our own, and you're really seeing it 2.5 million years in the past. So it really allows us, it's both a blessing and a curse. You never know how the universe looks like today, but you can actually see and measure how it looked like in the past. That really allows us to study the early universe and how it formed. Then there's also another small little fun caveat or like another consideration you have to do. And that is that the universe, as we know it, is not static. It's not something that's there. You have a galaxy here and another galaxy here. The universe is expanding and increasing in size. And just to show you how so we are physicists, we like to think of these diagrams and charts and so on. So how we typically think of it is that you can place the Earth at some point of this coordinate system, you place another galaxy at another coordinate, and then you let time go. And we know that the universe increases in size, it expands. So how we imagine is that it's really the coordinate system, so it's space-time itself that becomes larger. And you can see something weird happens with the light as well, that once this space-time expands, it also increases the wavelength of the light. So it's actually stretching the light waves as it transfers through the universe while this is happening. That means when we look at these very distant galaxies, light that will otherwise be ultraviolet, like the blue wavelength, the that will be in the infrared now. So all the light, even though it's very X-ray, UV, whatever it might be, in the early universe, we're always in this infrared wavelength. And just to show you a bit more scientific graph, and I'll explain just what's going on here. So in the bottom first, what you're seeing is an image of a galaxy. So it's taking at different filters. You can see the filters up in the top here. We have the visual light going from roughly 0.4 micrometer or 300, 400 nanometers, all the way up to 900 nanometers or so. Then you have the infrared light going beyond that. But then at the top, you're showing in gray, that's a galaxy spectrum, so how the light is dispersed. And this is taken, so it's actually a fairly far away galaxy, so it's seen roughly 10 billion years ago, how the light would look like. But then see if I start to shift this galaxy even further away, so you can see what happens in our measurements. So first, when you look at the top, you can see all the light is being stretched. There's really the same effect. All these photons are being stretched equally, so the UV photons are being stretched to the visual to the infrared, and so on. The further and further it goes away. And then at the same time, you can see the images I would take. So I would take images in different filters, typically called it. So these are actually Hubble filters. I made this impression here. And you can see that the galaxy just disappears. So all the photons that would otherwise be the ultraviolet and the visual are just gone. You only see it in the infrared. But that also means that if you were to look for a galaxy, and the galaxy you see over here, that's one of the first galaxies we'll be interested in. So seeing 13.5 billion years ago, when the first stars and galaxies are expected to form. And you see you can only really detect the light in the infrared. There is no signal at all in the visual. So you need something that's very good at observing at infrared or beyond wavelengths. All right. So just to show you this in the overall timeline of the universe and how this looks like. So what we're really interested in, what we're trying to push for, is that we want to detect the first stars and galaxies, which we believe happened roughly 300 million years after the Big Bang. We're trying to look at the chemical signatures of these galaxies, which elements are being formed and when, and so on, and also just how the first stars and galaxies form and under which conditions. But that really means that all these photons are being stretched to infrared light. Okay, so infrared, we need a big infrared telescope, and that is my cue to then show you this video. I'm not sure how many did see the launch of the James Webb Space Telescope. Was that few years ago? So this, I hope that it will start soon. Yes. So this was the last actual live images of the James Webb Space Telescope, JWST for short, being sent off into space. So after many years, almost 30 years of being built, we finally got into space in 2021, and they proceeded flying off. And I really like this graphic also just to show that the Earth is round. Just to, if you weren't up. For me, there's something, I don't know, magnificent about seeing an $11 billion telescope being sent off into space, just hoping that it moves nicely and everything. But fortunately for us, it did. So, yeah, that's very exciting. Yeah, so just to show you the highlights, so JWST is really the world's biggest space telescope. It's the biggest ever telescope we've sent to space. This really is something. And it observes mainly the infrared light, and it has this big mirror, so 6.5 diameter, 6.5 meter in diameter, gold mirror, coated gold. And the reason why it's gold and gold is because it's very efficient at reflecting infrared light. So when you look back at your mirror, like at home, it's mostly like aluminium or silver, because it's good at reflecting the visual or optical light. But with infrared light, you need something coated in gold. And then it was launched again on the Christmas morning in 2021. And just to compare, so I think most people here have heard about the Hubble Space Telescope, which has been up for almost 30 years now as well. Yeah, but just to compare, like the basic, so Hubble has like a primary mirror that's 2.4 meter diameter, which James Webb has a 6.5 meters, certainly a lot bigger. Hubble is in orbit around the Earth, so it has a temperature around 20 Kelvin, where JWST has to be cooled to minus 230 Kelvin, not Kelvin, sorry, 230 Celsius degrees, because it's an infrared instrument. So any kind of heating signature will basically just sort of contaminate the light that you're seeing. And then just to highlight again here, so Hubble sees in the visual and part of infrared, and And Webb has this part infrared, part optical, but mostly infrared light. And that's really the key to detect these first galaxies. And also just to add that Hubble, I mean, so the resolution, the kind of sensitivity you get with JWST is not necessarily a lot better. It's really just the shift in wavelength that's important. And you can see structures and galaxies and stars that you will never be able to see with Hubble purely because of the wavelength. Yeah. So okay. So just to show something like so what can JWST do? So the next best space telescope we had in infrared was called Spitzer. So I think that's actually decommissioned now. But that was the best thing we had before JWST. And Spitzer at some point took a picture of this star. So it's a star with some blobs. I think we can all agree that there's a bright blob in the middle and some other blobs around it, right? Then one of the first images that JWST took was at the same field. I think you can really appreciate the increase in resolution, right? So it's the same wavelength, same everything, but that's just the upgrade in the space instrumentation. And it really allows you to, well, first of all, see, okay, it's a star, that's all right. But all these little blobs, you can see that there's a galaxy, you can measure how far back it is, and everything like that. You can measure the morphology and the structure, everything. So I think that's a really nice upgrade. And in fact, JWST is so sensitive, so it's an infrared instrument, so a heat-based detector. So it's so sensitive that it could detect the heat signature of a single fly on the surface of the moon. I think that's pretty crazy. So that's really something like that's what we have now to study the first stars and galaxies, which I think is super exciting. Right. So the first picture the first actual science picture that JWST took was of this galaxy cluster called SMACS 0723 that I'm sure most people are familiar with, which is a galaxy cluster that's located roughly 5 billion light years away. And the reason that you can see this very nice image here, and I think most of you have probably seen this image version of it before, because I posted everywhere in 2021, 2022. No, not 2022. And the reason why I took a picture of this galaxy cluster, so you can start the question here, is because Einstein tells us that something interesting happens if you place a very dense and massive object in front of a light source like a galaxy, a background galaxy. So because the mass of this galaxy cluster will curve space-time around it, the light takes different paths through this galaxy cluster, but at the same time it also gets magnified. That means that whenever you have a galaxy or the light from a galaxy going around this galaxy cluster, you can see galaxies that you would otherwise not be able to do, because the light from that galaxy is magnified. Sometimes by a factor of 2, 3, but it could be factors of 100 or even thousands, which usually see galaxies that were potentially much further away, which is much more big, that you would otherwise do if you didn't have this kind of galaxy cluster. So that's the reason why we took this first image. And so I'll just leave you with this for 30 seconds. So this was the first image that I got in hand in the summer 2022. And you know that there's a lot of potential, very high redshift, very distant galaxies in this spot. And now it's your job to find it. So you get 30 seconds. You have to find something that's red, redshifted. It's mostly infrared light. It's slightly small because it's far away. And also, so small makes it not like a big structure. 30 seconds, you can see if you can spot something. Any good ideas? I see most of you are looking at the right place. So it's down here. Good job. So this little, so the guys, if you can't really see it, the guys in the front row can confirm that there is a little red dot in here, right? It's not something I'm making up. There is a little red dot in here. And the reason why this was interesting, so like the background image is like a composite image, so it's made of, like it's a color scheme of different filters put together. So what you see is really the same thing I was showing before. You try to image this field in different filters. You don't see anything in the 900 nanometers, so the first JWST filter. You don't really see anything at 1.15 micrometer, but then you start seeing something, a signal in all the other infrared filters, meaning that it should be a very prime candidate for being one of the most distant galaxies ever detected, and way beyond anything Hubble could even see. there was a very interesting galaxy that they were first explored. And also just to highlight that, like this image, people found this galaxy without using any kind of machine learning or fancy automated something. It's really like you did by eye, going around trying to figure out what seems most exciting and then trying to follow that up. And just to put it, so if you imagine this universe history again, so the Hubble Space Telescope, the most distant galaxy that could see was around just before 1 billion years after the Big Bang. But this guy we found with JWST was way beyond. So that was like the very first galaxy ever probably formed in the universe. So super interesting. If this was true, this would be one of the new record breakers. Surely tell us something new about the early universe. But just to highlight, so there's something else that was kind of funky about this. So again, sir, just showing another scientific graph, but just to explain it. So on the y-axis going up, you have the stellar mass, a particular galaxy, in solar mass. So that means on the y-axis you have 100 billion solar masses, 1 billion solar masses, 10 billion, and so on. And on the x-axis you have the age of the universe in millions of years. That means if you are over here, you're at Big Bang, then you go to 200, 250, and so on. Right? So this galaxy, GN-Z11, was the most distant galaxy we could detect by Hubble. That was seen roughly 400 million years after the Big Bang and had a mass of approximately 1 billion solar mass. Right? So then we can draw a line, we like to do that, saying that in our typical cosmological model, so the simulations I showed before, you start with a lot of gas that then can accrete and collapse into the star. You expect this green line or this green region to be the allowed region. That basically tells you something about you can collapse this amount of gas and with some efficiency turn it into a star, and that's like the most likely scenario. That was kind of the limit, but still okay. So yeah, so the red region would, in principle, maybe tell you that there's something wrong with our cosmological model, and also certainly that there has been more stars created than the gas available within that volume. We can cheat a bit and say, okay, so what if all the gas in our simulations is 100% effective at forming stars? We really take, like, if we push the physics to the maximum, we take all the gas and instantaneously turn it into stars. This is the maximum current we can get. So as time goes on, you can collapse more gas, but then you use all the gas for making stars. So you can see how some of the other galaxies put. So we also found this glass Z11. That was another distant galaxy by JWST. Glass Z13, another distant. Then this guy, most distant, so it's up here in the red. And this is really pushy, like everything. It uses up all the gas in the nearby surrounding. It's, for some reason, makes 10 times more stars than there's gas available, which is kind of strange. And they will really like break whatever we know about the early universe and how this structure and how this process, how it goes. Then just to add a few more, so we try to look for several other images now being made available. And they're also, some of them are okay, some of them are certainly up in this no region, which is uncomfortable, to say the least. But then again, so one of the first interpretations we did was just saying, well, I mean, we can't really weigh a galaxy, it's very difficult. The only thing we can do is measure the light. So you can just assume what if the light in these galaxies just shines more. Actually, there's more light than there's relative mass. And when you do that, you can move all the points down here. So again, sorry for a bit less scientific rigors. But it's this assumption that if you are in a very early universe and have a lot of gas and a lot of dense gas, you can create more massive stars that can shine more gas. So there is some motivation for it, but it's still like really pushing. And you can see even by pushing all the buttons we can, cranking all the knobs to the extreme, you still have these galaxies that at the border. They're really unlikely. So well, quickly after all the news I was saying on how we go in cosmology, I wouldn't really, I think I would first try to figure out if the measurements are right before, but this makes nicer headlines that astronomers don't know how to calculate this. But yeah, I think it was interesting enough that they had to figure out what was going on. And then what we did was we wanted to get a spectrum. We wanted to actually measure the redshift and the distance of this galaxy and figure out what kind of galaxy was it. I'm not sure how familiar you are with this, like a typical academic process. So typically what you do is that you write a proposal saying, I want to observe this galaxy, is potentially the most distant and super interesting. Then you send that proposal up, someone has to review it, and then if they agree with you, it's super interesting, they give you the time, then you wait 6 months, maybe a year, then you get the observations, then you get the data, you have to analyze and interpret it and so on. It takes you another 6 months maybe. Then you write a paper on it, you send it into a journal that also has to be approved and all this kind of stuff. And before you know it, it's like 2 years gone, right? So this, we took the spectrum, actually we tried to get the spectrum, another team from the US got the spectrum at least. So we did the only logical thing, and we published the result on Twitter instead. So three hours after the first data was taken, we published the first results on Twitter. And so this galaxy, CS1749, that was a tweet by my colleague Gabe Brown. And what he's basically saying is that this galaxy is not a redshift 16, it's not the most distant galaxy. And you can see that from the emission lines, these very strong lines that also match with some other galaxies in the field. So you can say that it's just some weird galaxy we haven't seen before, but are much closer to us. Still like 1 billion years after the Big Bang, so fairly early universe, but certainly weird. And you know, if there's ever drama in the astronomical community, it was like around this time. People got so mad in the US and all different teams, and we were just like, you know, it's public data, we do whatever we want. Not everyone agreed with that, but in the end they got that Nature paper when they were all citations. But they got a few likes, some controversy, which is good as well. But the puzzling thing is that the reason why we didn't really thought it could be anything else than a super distant galaxy was that it had a light profile that we've never seen before. Like the light distribution was just different from anything we've ever seen before. And just to show you an example. So in this right plot here, when you have the two downward facing arrows, that's the two filters where I didn't see anything. And then you have these data points, that's basically where all the light is, the red data points. And what we assumed is that you had the black curve, which is this very high redshift galaxy, that just drops off. But then in the back there's this, that was the actual spectrum, in the back in the red, there was the actual spectrum we got. And for some peculiar reason they had very strong emission lines, these spikes going up, but they just landed in the right filters, that it looked like the overall shape was this flat and going down, but instead had just this like reddish shape with some strong emission lines just in the right position, then it just looked different. But the emission lines were way stronger and way broader than anything we've ever seen before, so like there was nothing we could really account for in the models, but that's something we found. And curiously enough, when this happened, we of course started to look, is there other, like this, are there other super potential distant galaxies that are just built on the view? And it turns out there are way more, like there are a lot of these weird little red dots. And just to highlight that astronomers were not very good at naming stuff, so you can almost imagine what name we found for this. It's little red dots, that's what they are. But it seems like, so it's nothing like we've ever seen before. Looking at Hubble imaging later in the universe, looking at any kind of other, they're just not there. It seems like it's something unique that only appears in JWST data when you can look far enough and can look at these infrared things. So, yes. So that means that we really solved this problem of having a universe breaking early distant galaxy. But we have a new problem in that these type of sources, we don't really know what they are. We ask, like actually right now, I think if you follow that, in a week or so, 2 weeks ago, we will have a paper out that basically tries to solve all this little bit of problem, saying that it has to be a central supermassive black hole, not as massive as people are saying. So maybe I've heard some of these, like we have a supermassive black hole in the universe. These are just wrong. They're not that massive. They are maybe 10 or 100 times less massive than what people claim. But what's confusing people is that there's a lot of dense gas, super dense ionized gas around this black hole. We call it a black hole star, kind of central black hole, ionized gas around it. And that ionized gas just affects the line, it makes them broader, makes them more prominent, it makes this weird kind of shape that we just didn't see before. So we basically solve the problem, but we create a new, we have all these little red dots. We don't really know what they are, we assume we know, but it's just an entirely new phenomenon, and we believe it's basically the birth of supermassive black holes we've seen light in action trying to form. But not to discourage you entirely, so we did also find some of the most distant galaxies. It's not all like going around finding weird stuff. And this is one of the points that I'm very happy to give the talk now. So if I gave it a few months ago, I would say with great confidence this is the single most distant galaxy we've ever seen. It's called JWST Z14-0. But now, because I'm here and I'm now, we actually found a galaxy that's slightly more distant than that galaxy called NORM Z14 So you can see, so the redshift is 14.4, but the other is 14.2. So it's not a lot, but it's still 20 or so million years closer to Big Bang. And even though that's not like a lot, it's still 10% closer than before. And we're just seeing this galaxy now, 13.5 billion years ago, means that we're really uncovering the first 2% of the universe timeline. Right? So the entire year of the universe, we can start to dissect galaxies the first week of January, trying to see what they look like, how many are there, what are the characteristics, and so on. And the funny thing is that galaxy, we had this overall like uniform picture that all these distant galaxies, they kind of look the same, they have more of this gas accreting and so on. But this galaxy looks nothing like the other galaxy, completely different. Nothing is common. Same redshift, same distance, but it's just completely different. And I think that's very fun. And I guess something like the Cambrian explosion, if you're familiar with biology, you see this new wealth of life coming in. It is something like that we expect to see around this time. So there's no structure, no nothing that's settled and formed really in any kind of logical way. We just see explosions of light, stars, and galaxies like this. It's very exciting. But then, just to go get back to my own very personal work, what I note in some of these very distant galaxies, and it's a bit an odd diagram here, is that you can see you have this light profile going up, and then it suddenly decreases. Right? And now you just have to take my word for it. But when you zoom in to that region here, which is called the light alpha absorption, you realize that the absorption feature, how much light is missing, is much more than it should be otherwise. You expect some neutral hydrogen, this overall intergalactic medium around the galaxy, but it seems like there is a lot more light missing. And you can kind of compare it to, like you have a flashlight, for example, and you hold up 2 or 3 fingers or something, you can very easily see in the shadow if it's 2 or 3 fingers. You can very easily measure how much gas, how many fingers there are. And it's exactly the same thing we did. We had a very good idea of how the intrinsic galaxy should look like, but it just were missing a lot of light in that particular region where a lot of what we call primordial neutral hydrogen was supposed to be. So what we claimed in the study that we published last year in the Science was that we are now actually starting to see galaxy formation in progress. We're not just seeing galaxies, stars as they work, we can actually measure the material they form from this primordial matter, depending left over from the Big Bang. We can see how they accrete onto galaxies, we can measure how much there are, what is the assembly process, how does that drive the star formation, and all this, all these fundamental processes. And the great thing when you publish in Science and so on, then NASA will allow you, or will be happy to provide you with some nice visual thing. So it's not really like you should imagine the pixels you saw before, the red pixels, that's what they look like, but we imagine something like this. Nice to look at. And yeah, so this actually went to India. Times of India, I think there was some AI generation over. And remember that? I think it's a bit more obvious, but also I kind of like it in a way. It's a very, yeah, almost. But anyway, so that's how we, some AI tool, imagine this galaxy process. All right. So just to go back to the simulation, so that means that now we're actually seeing this process. We're not just trying to piece together different galaxies located here and there. We are actually measuring this purplish, faint, diffuse gas as it accretes onto galaxies, and can measure the exact process and how this happens. So we are really quite a lot further in trying to understand how the first stars and galaxies in the universe are formed. And just to put a bit of the simpler terms, what you compare to is that basically what we did with Hubble, and also in the beginning with JWST, was to look at butterflies, or look at galaxies, like we look at butterflies. So you can look at them in different colors, in different sizes, different shapes, and so on, in trying to figure out how the butterflies, where do they come from, how do they form, and so on. But what we're really doing now with JWST is that we're looking at the cocoon. Right? So we can actually measure the material they form from. We can dissect it, how does it impact the formation of this butterfly in the center, and how does it escape eventually from this cocoon and so on. And that's really what we can measure now with JWST. That was not possible with Hubble before. Yes. And then just to add that, so like most of this seems kind of like easy to do, and we have this access to JWST and this exclusive rights or whatever. But all the science are presented here, and all public data. So most of the JWST data is public. we compile into one database called the JWST archive, and it's right here on the webpage. So you can go in here if you want at some point and look at all the same spectra, all the same images, everything that JWST has produced so far. And we combine it here, we get it science ready, so you click and you get the exact same science data as how we look at it. So everything is just public and ready to use as part of this. And we try to make it super user friendly. So it's really just going in and clicking and searching like we're doing another web app or so on. I think there'll be a spectra soon coming. But yeah, so it's really just to highlight that that's really the vision, that it's public money funding JWST, so everything should be public to use. And yeah, so if you do that and you find something super interesting, remember to let me know first. Good. All right. So just to slowly wrap up. So I think we're really in a golden age of astronomy. So of course we have all the new gravitation wave and multi-messenger statistics and all this going on, super exciting stuff as well. But just like this, you know, in the material we can actually see it's super exciting as well. So we are really starting to uncover the first stars and galaxies. Measure them. We are really trying to measure this reionization of the universe, the last major phase change of the universe, happening roughly 1 billion years after the Big Bang as well. We can start to constrain information in heavy elements, so heavier than hydrogen and helium. And we can also directly measure the growth of the supermassive black holes if we take these new pieces of information into account. And we have all this suite of major space and ground-based facilities to do so. And I think it's nice to just end by thinking a bit about where we're going to be in the next 5 years. So a very short time scale still, that most people will remember what they thought 5 years ago. And just to put a bit in perspective, so 5 years ago, what we mostly had was the Very Large Telescope. The large telescope, called it Very Large Telescope. But what are we going to do in 5 years? So JWST will maybe only run for 10 years in total or so maybe we have to think what's next already. So we want to build something that's bigger than the Very Large Telescope. And of course, what do we call it? For the Extremely Large Telescope. Right? It's much bigger. So that is currently being built. And that in the top left, that's a webcam image taken a few, I think it's actually a few months ago now. But you can see like the main dome is being built. This is a visualization of how it's going to look like. And it's expected to be completed in 2017, 2018. Oh, sorry, 2027 and 2028. Sorry, you can have this complete structure ready. And just to put it in perspective, if you compare it to the Halbmond here, you can place that, and the main mirror will cover more than 50%, I guess 60% Halbmond here height. So they have a main mirror, a primary mirror of 40 meters. So it's basically like a big football stadium or something like that. The whole dome, and you have this 40 meter mirror. That's going to be the next thing, and I'm like in the, well, I guess in 5 years, in 2030, that's when we'll get the first science observations with this big telescope. So yeah, look forward to that. I'm sure it's going to be exciting. And that, I just want to say thank you.
Questions? I have 4 questions and a joke.
Good.
The
joke that I good.
How big are the images in megabytes that you were showing in the
Like on the web page?
Yeah.
I wouldn't download all the images, let's put it like that. But basically this, it's a very hard question to answer because you can actually download the science images, which is some megabytes size. But this takes all the images like a web page thing that just loads part of those images combined. I think it's easier to start from the web page, just move around and pick whatever images you like.
I really like the fact that you were talking about that you observe the space. I was looking at YouTube the other day and I found a video from 1997 and it seemed to be originated from NASA, the public YouTube channel that they have. And they were showing some like plasma and I downloaded the book by Robert Campbell, do you know him? He talks about like plasma in space.
Yes.
Electrons that are kind of looks like a package is.
Okay.
Do you observe those kinds of things or am I just being
So yes, some kind of discs. That what you're saying? Some kind of discs. That what you're saying?
Packages, it kind of looks like it's alive, you know, I mean, it's like a, he's showing like images of plasma and he wrote a book
Yeah. I mean, yes. I mean, so typically on the scales we observe here, it's long scales compared to human lifetime, so we don't really see. But there are like lines from plasma, so that's basically what we observe in these, what we call emission lines, that we see, and that's what we use to figure out which kind of filaments are there.
And then I was thinking, I'm just a simple public servant, and I don't get it. It seems like a paradox for me when you talk about what looking in the past.
Yes.
I don't know, I was under the knowledge that the quantum leap is also a real thing, that you maybe just wasn't fully real, that you were always looking in time. And also, if you're always looking back, is the time defined from the planet, and everything is cast from my point of view, or can I ever look into the future?
No, you can't ever look into the future. And that's the easy question to that. Well, I think there are two effects at play here. So there's one, which is just like, we have time, and we decide to measure it in years and seconds and so on Earth related to something. Of course, like time itself doesn't really care what we call it. But there is an actual time, just basically this photon light travel. You can deduce that it has to be X amount of years. Of course, there's something that happens when light gets close to something that's massive, like a black hole or even a galaxy cluster or something, where there's some light. Well, so basically the light you're seeing on the time it pokes is different because of Einstein's relativity or general relativity, saying that the light, the time is so very different. That is different effects. So now when we're talking about time in this, we're just purely talking about something that happened some time ago. When we don't these relativity or exotic effects.
But is there any direction where you will see more past, or can you always look in every direction from the planet, and then you will always see?
Yes. So our assumption and observation seems to support this is that the universe is the same everywhere all at once. So it doesn't matter which direction you look at, you will always see more or less the same.
Well, I'm going to have to joke,
Good.
saying that you were bad at naming things.
Yes.
Maybe you should talk to some of the big pharma marketing, because they seem to have gotten it right.
Right. Yeah, maybe we should get out.
But yeah, thanks for the presentation.
Question over there?
Yes, hi, Cameron, a PhD student in geology. I had a question about the James Webb Space Telescope Deep Field. There was a paper that came out recently about looking at spiral galaxies and how they rotate in this early universe. And like you said, the universe is expanding in all directions equally, but they showed that the spiral arms were rotating. Some were rotating more counterclockwise than clockwise. And they suggested that this might be due to a rotating universe. And one of the reasons you can get a rotating universe is if we're living in a black hole. So, have you what are your thoughts on this?
Yes, so I have two versions of the thoughts. One we can share, I can share later after beer maybe. The other, a bit more professional, is that, so I think, unfortunately, so the rotation and all this is certainly true. That's a fact. The guy, the team that's been publishing, I think it is, they have a way of reinforcing their theory that they want this picture. But with that being said, so there's clearly a rotation, and it seems like some studies suggest that galaxies seem to rotate more in one direction than the other, which is weird, right? So there seems to be an actual, an angular momentum in the universe. And why would it do that? It should be the same. But again, it's a bit, it's still uncertain whether that's true. But related to your point, so I'm not sure if that evidence directly points to living in a black hole. And see, but there is a fun exercise you can do, like in first year physics, astrophysics, is that you can basically calculate the mean density of the universe. So it's easy to count out the galaxies, black holes, and so on. And you take what we call a Hubble radius, which is the size more or less of the universe. And when you do that, you get the mean density, you get the same mass as black hole. So there is this weird thing that's seemingly consistent with a black hole, but it doesn't seem like it. And there is certainly information going around that will kind of contradict this. Yes, that's fine. This?
were actually, redshift within that it was moving to the right direction.
Oh yeah, the one there.
Why did some of that data fall off, basically, on the vertical axis? So the light that was furthest to the left kind of seemed to drop off.
Yes.
Why is that?
Yeah, so there are two things to answer to that question. So you can see, I'll just run it last time. So you can see there's light falling off at the end here, and then shortly after this, there's also light falling off at another direction, or another place in the spectrum. I'll just stop this so we don't get right. There are two things happening. The first drop off that you see here is basically it's called the alignment limit. That's why there's no electronic transitions in hydrogen to need, like an electron jumping down, sending on right. So that energy of that wavelength corresponds to that limit. There's no particles with enough energy to bound to hydrogen. But then once you go into this slightly higher redshift, so more distant, you actually start to see, or you start to get an increasing amount of this neutral gas in the intergalactic medium. When I mentioned this reionization phase, that's basically because we believe that our observations support this, that once, after quickly after Big Bang, you have this primordial neutron atomic hydrogen. And once you start making the first stars, the galaxies, and maybe also supermassive black holes, they'll start to ionize this neutral gas. That means that when you see this, you have a lot of ionized gas where the photons can easily run through. Once you go further back, you have a lot of neutral gas that absorb all the transitions. So it's basically because you start, like the reason why you see this increasing drop is because you see an increasing amount of neutral hydrogen in the intergalactic medium. Yeah. That's basically the technique used by
you mentioned the little red dots.
Yes.
They are basically accreting giant black holes.
Yes.
Does that support the theory of the direct collapse?
I don't think it excludes the theory, it supports it. I think what we really have to do now is that we have to be careful that we really need this direct collapse to explain the very high mass black holes we were seeing. But now the mass is not really that high, but that's what we predict that it can be that high. So they're all perfectly normal as we would expect. So you don't really need this more exotic direct collapse scenario. You just need standard collapse. There are still, I think it's still undecided whether you need it. It is a bit more rapidly forming, could be collapsing, whatever way it is. So you might need it still, but it's not as crucial as before. It's not really something you definitely need. Now you just need whatever you see now, basically. Amount of gas, amount of stars, so I think, unfortunately, most of the exotic dark matter black hole theories were not debunked, but they are not needed anymore.
I have a question about this slide, actually.
Yes.
So most of the filters here look something like a boxer function and have a W at the end. But there's one with LB at the end with a big about 12.9.
Yes.
Which is more like it has more triangle shape. How is it different from all the others?
So in principle, it's super arbitrary in many ways. So the W just stands for wide, so it's a wide filter. The LP is, I think it's long something. I can't really remember what it stands for. But it's super arbitrary. Some of these filters are made man-made by just, I want this filter to look something like this. And typically you define these broad filters to look like broad, like coarse images. And then sometimes you want like a super narrow filter just in this way, so you know that whenever there's something in there, you know there's like some kind of emission line, something bright that we see.
Is there a particular feature of that wavelength that you'll be working with?
Well, so in principle there could be many features at different wavelengths or different. So I'm not sure if there's something particular here. But you could imagine that when you move this, if I move this galaxy, you could much more finely say that if you now don't detect anything in that narrow filter, you're much more certain of what the break is. So it's mostly like that. do this more finely sampled material you just want to store.
Any more questions? All right, my turn then. Do you think some of these really old galaxies still exist?
Yes, certainly. Well, it's an easy yes, but I don't want to keep on it. I think what we'll see is that most of these galaxies will likely merge at some point, and it's a good fraction of them will merge. So it's basically what we call like a standard cosmological model, like a hierarchical structure formation. Is that you start off with a small galaxy, but then merge together, and do all that. That's how we build up to these massive galaxies. Like you kind of see the same as like the large and small, like thousands kind of streams. There's been like some merge activity. It will exist, but like in a different or combined form. I have jokes in. Good. What do you call M&Ms that want to go to school? What do you call M&Ms that want to go to school? Yeah, thank you.
Thank you all for coming, and see you December 3rd, right here. What do you say?
Yeah, so